engineer and technical lead of the operational DER management team at the AEMO. In 2006, Philip received his BE in electrical power engineering and bachelor's in business administration from ECU. From 2016 to 19, he was with DigiSilent Pacific building power system models, performing studies and undertaking commissioning work for some of the Australia's largest industrial load customers, while also delivering training courses for DigiSilent Power Factory and Station. Since 2019, Philip has developed load and DPV models for dynamic system studies in NEM and is also a member of international working groups aiming to advance the current state-of-the-art modeling future power system. I will hand over the mic and the presentation to Philip Brandick. Philip, welcome to the session.
Excellent. Thank you, Hyatt, and thanks everyone for joining me today. Can everyone hear me okay?
Yes, we can hear you okay.
Excellent. So I might just share my screen and kick things off if that's all right.
Yeah, perfect. Thank you.
Okay, can everyone see that?
Yeah.
Awesome. So I'll kick things off with the title of today's presentation. So it's building dynamic composite load and distributed PV models for the national electricity market. Don't need to go into too much detail about who I am, given the awesome intro by Hyatt. So thank you for that. What I will say though is if anyone has any questions, please feel free to just jump in throughout the slides. I've done a bunch of these presentations and it is a lot of content. And it's 2 years of work being compressed into 3 30 minutes or 40 minutes. So rather than waiting to the end, please feel free to just jump in and ask away whenever you can think of something. So without further ado, I'll kick things off. So today I'll be going through the composite load model structure and how we selected the parameters, the DER model structure and parameters, the validation of the two models, some of the results that we've received from the validation, and then the benefits of using the models and the next steps in terms of our work from the operational DER management team perspective. For those that don't know what DER is, it's distributed energy resources and encompasses things like rooftop PV, your Tesla Powerwalls, for example, and other distributed resources. So electric vehicles would fall under that category as well. So I guess the first question that needs to be answered is why do we even need to model load and distributed PV? Who cares? So the answer to that is we've got, as everyone probably knows, we've got a changing energy mix. And because we've got an energy mix, we need to be able to capture that changing energy mix accurately, especially if you look at the bigger picture and see what's actually happening. So in terms of load, devices that were once motor driven, such as your washing machines or your dishwasher, are increasingly commonly becoming inverter driven. And from the DPV perspective or rooftop PV perspective, you've got 25 million people, maybe 5 or 10 million homes, and most of them have, or a whole bunch of them have, rooftop PV. So there's obviously a dynamic response that isn't being captured by the existing models that we have available to us today. So the energy market operator has been, and my team specifically, has been working on building these load and DPV models with a view to model a whole bunch of distributed energy resources so that people on this call, network service providers, network operators throughout Australia are able to use these models, and it gives international network operators and service providers a framework as well. So starting with ZIP, for anyone that's used PSSE before, you'll notice they're all ZIP models in PSSE. You can download a PSSE case from OPDMS. You can find a link on AEMO's website. And obviously the ZIP is constrained inherently by what it is. It's a zip model: constant current, constant impedance, constant power, and then the breakdown of those. But if you want to do something like a motor starting study, you're not going to use a zip model. You might want to use a model where you can capture that aggregate response more accurately. So you might use a dynamic model like a Sim6BL model in PSSE, and then you can accurately or more accurately capture the dynamic response of that single motor. So that's your zip plus IM, and that's prevalent in the US. And then if you want to add another level of complexity, you would go to, I guess you could call it the ultimate level or ultimate representation. You can go and build bespoke models. And essentially that is a model that's as detailed as you need it for the study that you're doing. So the user can model each motor load and each electronic load in the national electricity market and the Swiss, so the NEM or the Swiss. But I mean, we'd be here forever, right? So especially because the NEM operates one of the world's longest interconnected power systems. So AEMO have come up with a hybrid approach to that. So we're working with NSPs, the ones that are proactive anyway. So we're working closely with PowerLink and Electronet to help with the development of these bespoke models in critical areas like the Surat Basin in Queensland. So the Surat Basin is the LNG area, and it's a significant amount of load in Queensland. So we want to make sure we're modeling that as accurately and as accurately as possible. And then we adopt a composite load model, as you can see. Oh, I have a little bit of back chatter. I'm not sure if people are no longer mute.
I'll mute everyone, and then Philip, can you unmute yourself?
Yep. Can't do it.
Please
okay,
unmute.
Now I can. Yep.
Okay.
Okay, cool. However, can people unmute themselves if they want to ask questions? Is that possible?
Yes, they can unmute themselves.
Okay.
Yes.
Okay, cool. So where was I? So the composite load model, bespoke models for those critical areas, and then the composite load model to capture the rest of the end use loads in the NEM and the Swiss. And the reason we use the composite load model is because it provides a greater level of flexibility in that it captures the distribution network and it actually captures a variety of loads. So if you look at compare it to the complex load model, it's a little bit more intricate than the complex load model itself. So then moving on to the composite load model structure. And for anyone that's ever used our OPDMS PSSE case or downloaded a historic snapshot, you'll know that we have very, very little distribution network modeled, and you can imagine why. For anyone that's been modeling, distribution network level data, you'll know that it's very time consuming, and if you have to do it for the whole of Australia or at least for the whole of the NEM, you'll be here forever, and you'll probably handball it off to a grad, and the grad will probably go after 2 weeks and be like, I don't want anything to do with this. So we use the composite load model. And it's an aggregate model. We've got an aggregate distribution transformer and on-load tap changer connected to the transmission bus. We've got a distribution bus here as well. We've got a substation bus capacitor at that distribution bus. We've got an equivalent circuit, which is represented by a series impedance that you see here. And you've got your shunt compensation there. And then you've got a load bus as well with a bunch of motor loads, electronic loads, and static loads. So then you've got three-phase motors, a single-phase performance motor model, and electronic and static. So motor A is representative of air conditioner, compressors, and other constant torque loads. Motor B represents your ventilation fans and other loads with a torque characteristic that is proportional to speed squared. You've got motor C, which is also three-phase loads, but in PSSC, by the way, we can model these as single-phase or three-phase loads and just lump them in that sort of motor C section. Motor C represents water circulation pumps, and again, their torque is proportional to speed squared. Motor D, this one's an important model, especially in the US, because the majority of their single-phase capacitor start loads are air conditioners, and they have huge transient network effects as a result of these single-phase loads, especially when you're considering the fault-induced delayed voltage recovery. And then you've got your electronic load here as well. So they're your appliances, your computers, your microwaves, your TV, connecting your mobile phone at night to charge. And then you've got your lighting. And that static load section here just represents the remainder of the unclassified aggregate loads. Any questions so far?
Just a quick question. Do any of the loads reasonably represent variable speed drives?
That is a great question. And reasonably represent, the short answer is no. Represent, yes, they're lumped in the electronic load section. But we know that based on studies conducted, extensive studies conducted especially in the US, that the first part of a VSD, mind you, we're talking about a aggregate model. The first part of a VSD during a voltage disturbance event is accurately captured, but as that voltage recovers, the current would be limited to 1.2 times as it returns. So that's like the average that these studies have shown. So the current gets limited to 1.2 times on the return path of that end of that voltage disturbance, so following the fault. So that's not actually captured. And we see that in our validation studies, that we're not actually capturing the complete dynamic response of a VSD in that electronic load model, because it doesn't represent that post-fault effect that VSDs have.
Thanks.
Yeah. In saying that, the WECC and NERC is working on integrating a VSD model. So we're in talks with them. They've got one built. They just don't have one built for PSSC. So once that's available in PSSC, we'll roll that out in our composite load model. Okay, moving on. So why would we adopt the composite load model other than what we've already discussed? So the ZIP model, number one, it's unable to represent load disconnection. And number two, it's this combination of constant I, P, and Z, and it worked well for AEMO for the last 20 years, and plenty of consultants and network service providers can attest to that. But there's a few critical things that we outline here that tilts the scales, if you will, in the direction of the composite load model. So it's able to represent this three-phase and single-phase motor load and power electronic load and static load. It's also able to represent the disconnection of these aggregate motors and power electronic loads. It includes a distribution network circuit or equivalent components, and it has the ability to replicate, if done correctly, the dynamic response of these aggregate loads as well. And it can also be implemented alongside the DER model. So there's plenty of reasons to go down the path of doing it. It's just a time-consuming and I guess you could say time-consuming, and it's a hair pulling out of my head process. But you know, the team's got there 2 years later, so we're very happy with that and happy to be finally rolling it out. So in terms of how we select the composite load model parameters, there's two key things. One is the rules of association, and number two is the load characteristics themselves. So I'll try to go through these few questions that you see here. So what are ROA, or rules of association? How do we categorize loads? What are load characteristics and why they're important, and how they impact the load model? So starting with rules of association, And I've used a residential end-use load example here. And working back to front, basically, rules of association, it's important to get the rules of association right when you're representing the mix of loads in the NEM or the SWIFT, because without that accurate representation, there's no level of model tuning that will actually give you a truly accurate dynamic response in system studies. And even if you go through all the hard work to get the rules of association right, because there's probably 100 million loads, different end-use loads connected in the NEM and the SWIFT, it's almost impossible to capture it, but we try to do the best we can with the information available to us. So, for example, in this case, electricity consumption, which we have data for, is broken down in residential, commercial, and industrial sector, so 3 sectors. We know within the residential end-use load sector, there's a bunch of these loads, and I've just selected, some of the sort of more energy-intensive loads or more commonly used loads. So we can split the energy consumption in the residential sector by these end-use loads using data sources, which I'll cover in a second. And then using the rules of association, we know that in Australia, refrigerators are made up, for example, of 90% motor D, the single-phase cap-start motor, and 10% power electronic load. And we also know through some of the consultant work that we've done that mix is also changing. So those motors are being phased out and they're being largely inverter driven moving forward, obviously with price to match. So then in terms of rules of association and how we sort of get there, so we start with the underlying demand data for those 3 sectors. You can find that in the ESU, which is the Electricity Statement of Opportunities that the Energy Market Operator releases every year. And then we split those demands between the 3 sectors. As you can see here for the industrial sector, we updated the rules of association for some end-use load types based on NSP consultation. We spoke with a bunch of TNSPs and DNSPs, so transmission network service providers and distribution network service providers. And one of the things we found is that the rules of association that we were using from a Lawrence Berkeley study, as you can see here, LBNL, Lawrence Berkeley, that one there was misrepresenting the amount of power electronics loads or VSD loads in the industrial sector. So we changed those rules of association to be more in line with some of the data that the NSPs had. Obviously, keeping in mind that between, say, mine sites, a very old mine site versus a very new mine site, you're going to have very different makeup of those end-use loads, largely being, inverter driven for a newer mine site, and only when a motor gets replaced may you consider a VSD, or if there are financial incentives to add a VSD, then you go down the VSD route. So that's industrial loads. We use the NERC documentation and Lawrence Berkeley studies in consultation with NSPs. For residential loads, that was an interesting one. We used data from a 2014 Australian government residential baseline study, where they broke down all the loads that we would typically see in a household, and on a per region basis, what proportion of each load makes up the total energy consumption of a household per region. And we also changed or tweaked those rules of association in consultation with NSPs and with new findings as well from our consultants. As I said, the dishwashers and washing machines becoming power electronic or inverter driven devices. From the commercial load perspective, this one was probably the most impressive. We hired a consultant, so Delta Q. They're data analysts and they're fantastic at what they do. They used our underlying demand data to break down the loads by sector. So say commercial load, of course, but then within commercial load, you've got commercial offices. And then they further broke it down into subsectors. So within commercial offices, you have exhaust fans, you've got cooling towers, you've got light and small power. And then we know, according to our rules of association, that exhaust fans make up 90% motor B and 10% power electronics load. So then say, if it was just exhaust fans, 10 meg of exhaust fans, it would be 9 megawatts of motor B and 1 megawatt of power electronics load. Any questions?
In terms of domestic loads, have you considered the rise of electric vehicle charging and the major impact that could have?
Yeah, that's been playing on our mind quite a bit. It's interesting you say that, because our next step at AEMO is to build EV models or battery models, but those battery models could be applicable based on some preliminary studies that we've done to EV models as well, because it's a battery bank at the end of the day. What's interesting though is how the adoption of EV, which is, I think last time I checked, was sitting at like 350,000 vehicles in Australia and growing. I think the growth rate was 80% a year. Don't quote me on that though. I haven't checked it in a few months, but those EVs are say 60 kilowatt hour to 150 kilowatt hours, whereas a typical house might be 30 kilowatt hours per day. And you can imagine a EV being used to travel around the city, etc., all day, come home, plug in to charge, and you've got the equivalent of 5 houses consuming power at that one residence. So you can imagine the sort of end-use load mix change, and why we have to why we have to build battery models on top of load models, on top of distributed PV models, on top of the other models that we have.
Got another question. Shouldn't we take VSD-driven motors as VSD? Means the motor part doesn't take part anymore as a normal conventional motor.
Yeah, exactly. So those power electronic loads that we've currently got modeled as VSDs, so we'll take it out of that power electronics load component and put it in a separate VSD component. So it's not that we have VSDs modeled as motors here. We have them modeled as power electronic loads with a constant P and Q. Well, it's linear with voltage. But yeah, we're moving one step further once those models get released by the WECC to then have a separate VSD model.
Thank you.
Cool. So then load characteristics. So to get an accurate response for a load model, it's important to set model parameters that are representative of the loads that we have in the NEM and the Swiss. There's no point using the US parameters if they're not applicable. So one of the ways we did that for the motors, at least, is compared the motor standards themselves. So in the US, or it's the NEMA standard, and in Australia, we compared the AS 60034 standard, which is based on the internationally adopted IEC 60034 standard. And then to confirm applicability, we compared things like motor size, motor efficiency, frame dimensions, torque speed curves to make sure they all made sense and that we were using appropriate base parameters. In terms of the motor D component, that's a very important one, as I mentioned before. We harness the expertise of energy efficient strategies, another consultant, to better understand, first of all, where these motor D loads were, and what sort of role they play in terms of dynamic response or for voltage disturbances. So EES, energy efficient strategies, determined that the ACs, our air conditioners, are largely inverter driven. We knew that, we just didn't know how much. So EES broke that down for us. And in fact, our single phase residential refrigerators make up the majority of motor D, and motor D accounts for about anywhere from 3 to 13% of the total load in the NEM and the Swiss, depending on which region you're looking at. Moving forward, the composite load model actually reduces the amount of motor D based on sales data and projected sales data, that is, going into 2030. So you will see, using the composite load model that we've got, if you plug in a date that's 2025, say, the amount of motor D comes down with an equivalent increase in the power electronics load. Okay, so before I go on to the DER model, any questions with the load model? No, sounds good. I'll kick things off with the DER model. So the latest approach recommended by NERC and the WECC is to split the model between utility DER and residential DER, plugging in the utility DER here and then your residential DER at the load bus. When AEMO started modeling the composite load and DER models, the idea was still in draft stage. So we modeled it at the transmission network, had a lot of feedback from NSPs saying, is that right? Should we be modeling it that way? And our preliminary findings have shown that it doesn't make a big impact because it is an aggregate model. However, international studies have also shown, in this case, the PJM, which is a regional transmission organization in the US, says the DPV model is minimally sensitive to feeder impedance assumptions. And EPRI says the behavior of the DER model is not expected to vary with feeder voltage. So perhaps the way that we've got it modeled here is okay, and we don't need to split it across this utility distribution bus and the load bus, but we will be testing that out in future studies. So in terms of the DER model implementation, so the WECC and the NERC actually released what's called the DERA model, and it provided that initial benchmark representation of rooftop PV and inverters. However, AEMO identified that it didn't represent several of the characteristics of DPV that were known to occur in the NEM, primarily because our testing wasn't as stringent as it should have been, and the AS4777 standard wasn't as, I guess you could say, detailed as it should have been. But the latest standard, which will be implemented in December or January this year or early next year, aims to sort of capture these and standardize these differences. So we developed a user model based on that DER model, which we termed DER AEMO 1, and it gives us a little bit of additional flexibility to adopt, adopt future changes to DPV parameters, but it also gives us the ability, and NSPs the ability, to play with their existing technical requirements for inverters and see what works for them the best. So they can use our model, play with some of the parameters, make sure they understand what they're doing. If that all goes according to plan, then they can change their technical requirements, which each NSP has. So here's the simplified block diagram. Just please note that there are way more control block options available here. We just haven't shown it. Otherwise, it would just be a bit of a mess, and I really wanted to focus in on the ones that have been implemented. So for example, you don't see under frequency droop control here. And the reason is it hasn't been implemented by residential DPV. And that is because the AS4777 standard doesn't require it. So we've got over frequency droop control, we've got constant power factor and asymmetric volt var control if required by the DNSPs. And then we've got this trip logic as well. So the trip logic, I guess, is probably the most important block that we needed to consider. And we've included things like 13-stage under and over frequency protection, noting that the AS4777 doesn't have 13 stages of frequency settings. However, we know that all inverters aren't created equal, and because of those AS4777 standards, the 2005 and the 2015 standard, being limited in detail, it was a bit of a, I guess, a Wild West up until this latest standard that is being released. So we know there's various inverters that trip on different under and over frequency stages, as well as under and over voltages. And then we've also included rock-off protection as well, given some of the findings from UNSW. UNSW is an ARENA-funded project which bench tests a bunch of inverters, and they've bench tested 30 inverters now, which make up, or close to 30 inverters, which make up about 25% of all inverter models in the NEM. So we get a pretty good idea from them how these inverters behave. Any questions on the DR-AEMO 1 block diagram? Nope. Cool. So to select DR parameters, I guess we got to go through a few things: inverter composition, inverter trip setting, and inverter control parameters. So I'll go through each one individually, what they are, why didn't we just use the AS4777 standard settings, and why do DNSPs have different control parameters and what they are as well. So in terms of inverter composition, it's important to get the mix of inverters right. So we know that there's plenty of inverters in the NEM. You just have to look at the CEC list to know that there's, you know, over 1,000 different accredited inverters that can be installed. We need to understand which ones they are, which standard they're applicable to, and whether they're also compliant to that standard. And then you add to the mix DNSP controls, like whether volt bar settings are enabled or disabled, etc. So a bit of a process to get to inverter composition. So we looked at the DPV capacity data from our internal team, and we looked at it from the perspective of a connection point ID. So a connection point ID is basically just a representation of where that asset is. So geographically, that is. So the connection point ID, but that geographic representation is not there in PSSE. So once we know where the DPV is geographically, then we can match between connection point ID to PSSE bus numbers, which was a painstaking and excruciating task. And one of the first things I did when I got to AEMO was start trying to put this map together, and it took a while, but we got there in the end. And then once we've got the PSSE buses mapped, we can take a look at the APVI, so the Australian Photovoltaic Institute, and look at their time series data by postcode. And by that, I mean the installed capacity by postcode, and compare it to our PSSE map now that we've built, and just make sure that we're sort of putting those inverters at the right place. And then we use the Clean Energy Regulator database as well to understand the types of inverters that are installed for a given region. So whether they're, you know, in 2019, on the 1st of Jan 2019, there might have been 13% applicable to the AS4777 2005 standard, and then the remainder applicable to the 2015 standard. But now, and another reason that's important is because now we've got to consider 2005 standard, 2015 standard, NSP controls, so whether they're volt bar enabled, etc. And then we've also got the 2020 standard, and that of course makes up the inverter composition. Moving on, the inverter trip settings. So these are the main sources of information there, and then I've broken it down here for you. So one of, I guess you could call it a godsend, because it was absolutely amazing the work that UNSW could do and the level of information that we could get from them working closely to make sure the tests that they were doing were able to inform the parameters that we were trying to get. So in terms of frequency parameters for 2005 inverters, we looked at a frequency setting survey of inverter manufacturers that was done in 2016, I believe. And we also looked at the solar analytics data set to inform the frequency set points for the 2005 inverters in the DER model. When I say solar analytics data set, I'm sure there's a few people on this call that probably have the solar analytics system set up on their home to monitor how their PV system is doing. We use that data to understand the amount of PV that was generating and compare that to the data that we have as well. And obviously that takes into account things like weather, cloud cover, that sort of thing. But we also use it to understand for a given disturbance, say a 30% voltage dip or a voltage sag, how many of the inverters have tripped, and then extrapolate that out to the rest of the region. For the 2015 inverters, in terms of frequency, we noticed that they were tripping, but they were tripping about half as much as the 2005 inverters, and they also weren't tripping in line with the 2015 standard, which is why the 2020 standard came about. Again, also using that solar analytics data. For undervoltage events and rate of change of frequency, we used UNSW's data, their bench testing results, where they could apply an undervoltage, a voltage sag of 10%, 20%, 30% for 80, 100, 120, 220 milliseconds, and understand the inverter behavior that way. Same as rock-off as well. And then for overvoltage events, we used a combination of the AS4777 standard and then tuned the model to get an appropriate response. So that makes up the inverter trip settings. In terms of control parameters, Energy Networks Australia has an awesome document that has the volt bar requirements of the DNSPs. So we use that, and based on those control parameters that the NSPs have individually set, we've built like an aggregate representation of their response mode settings in the DPV model. So we use this data to determine things like volt bar settings, and by understanding the amount of each inverter that's installed, we can have variable volt bar settings. So, in South Australia, volt bar was enabled in perhaps 2019, I'm just spitballing here. So anything before that doesn't have these volt bar enabled settings. So if you input a date in our DPV model that says 2016, you're not going to have these volt bar settings. If you input a date, on day one, since those settings were enabled, you're still not going to have any because it makes up 0%. But down the track, those volt bar enabled inverters start to make up a bigger portion of the grid. Any questions? Nope, I'll keep going. So the model validation, these last few sections are quite quick, but how do we validate the model? So I'll just do it in 3 steps. So the composite load model parameter tuning. So the composite load model, we looked at 15 voltage and frequency events from 2017 to 2021, because that's where we had the most data for. And we analyzed nighttime events, daytime events, focusing specifically on nighttime events predominantly for the composite load model, so that we can exclude the behavior of distributed PV. So we looked at 15 of the most significant events to validate the model against. For the DER model, we looked at 7 events. We looked at solar analytics data to determine the amount of DPV that disconnected for a given disturbance, date and time, to tune our voltage parameters. And then similarly, we looked at 3 frequency disturbance events to tune our frequency parameters using that same solar analytics data of disconnection and curtailment. So to summarize the data collection for the validation studies, we of course need HSM data. If we're looking at trying to better understand the dynamic response of these models, we need HSM data so we can look at the dynamic profile, the P, the Q, so the active power, the reactive power, the voltage, the frequency. We looked at SCADA data to get the load response. Now, SCADA data, as you're all aware, it's 4 seconds, it's crap, it's not time synced. So there's a bit of trial and error there, and there's definitely some error in the operational demand change when we look at that SCADA data. But in any case, it's what we've got to work with. Then we looked at the solar analytics data to get our DPV disconnection or curtailment estimates in the case of a frequency event for each of the NEM regions for a given disturbance. We looked at DPV capacity factors. So that comes from our NEO or WARE database, which some NSPs may have access to as well. But essentially, we might have, say, 1.5 gig of inverters in South Australia, and of that 1.5 for a particular disturbance day and time, there was half of them, so 750 meg was operating at the time of the event. So that's where the DPV capacity factor comes in. And then, of course, to actually get our models up to scratch, we needed to understand the installed capacity of DPV in each region, Western Australia, South Australia, etc. So we used our internal team, our connection point forecasting team. We used the data from the DER register, which is still being updated. It's gone live. It went live about 12 months ago, but it's still being updated by NSPs, and that's a work in progress, but we used what we could. And then the APBI's time series data to make sure that we've accounted for all the DPV. So looking at a validation example, I know there's a lot going on here, so I'll try and break it down, but this is just a validation example for the 24th of Jan 2021 event, which was a voltage or under voltage event, obviously from the voltage plot in South Australia. There were 6 faults in the area, and it resulted in 3 transmission lines being tripped. Of those 3 transmission lines, we modelled the last 2 trips. The first one wasn't a significant trip, and also it was minutes apart, and the time it would take to run those studies, it wasn't feasible. So looking at the voltage response, I mean, I'll just go through the plot quickly. So the HSM data is what we're comparing it against. So that thing in purple. Light blue is the existing zip model. If we never implemented the composite load and DPV models, that would be the response that you see from the zip model in PSSE. Some NSPs have asked, can we use the zip model and the DER model because there's still a little bit of reluctancy going on in terms of the understanding how one could possibly have captured the end-use load mix for Australia. So that we've also plotted that as well. And then there's the response of the composite load and DER model. And when I say the response, I mean seen at that bus, this is the dynamic response for an under voltage event. So in this case, in terms of the voltage overshoot, you can see that all models marginally overestimate it, but stay within our normal operating range of 0.9 to 1.1. You can see in terms of the voltage recovery rate, the composite load and DER model are most representative of the observed HSM data, while the ZIP and ZIP-DER models quickly snap back. And in terms of steady state voltages for this particular event, they're all pretty good. I mean, you don't see the steady state voltage here, but we ran the simulation out to 60 seconds in this case, and it was a good response. From the active power along this feeder, so this is the TIPS B to City West feeder, which is Torrens Island and City West. So you can see, I mean, you can't really see the dynamic response because the plot's 45 seconds long, but in terms of the active power, during that transient period, there's 2 faults here, 1, 2. During that transient period, the composite load model has a most comparable trajectory to the observed data. although it slightly underestimates peak flows during the fault. I won't go into too much detail about the implications of that because they all underestimate it, but it should be noted that the CMLD plus DER also slightly underestimates that peak power flow. Similarly, just in this disturbance, not for all disturbances. Similarly, for the reactive power, you see that the composite load model and DER model has a similar trajectory to the HSM, although again, it slightly underestimates these peak flows during the fault. Plenty of reasons why that could be. We don't have we have a few under-excitation and over-excitation limiters modeled in PSSE, but I wouldn't put a bet on it that they're modeled accurately because, or in line with how it actually behaves, because it's never been a pressing issue from AEMO's perspective up until recently. So reactive power responds quite well. As you can see, the steady state power is a lot better represented than, say, a zip model or a zip plus DER model. Similarly, the active power is better represented as well. In terms of DPV model, I've got the solar analytics estimate here, which is that darker line. And then we've got a range of uncertainty in green for this event. So we know that for this event, the DPV prior to the event was about 550 meg, and it went down to 450 meg, so maybe 113 megs of disconnection, but it could have been anywhere from 68 to 135 meg. And the reason why I put these results in there is to highlight the uncertainty and the need for more accurate data, whether that's HSM data at the transmission level, HSM data at the distribution level, solar analytics data, more accurate solar analytics data, or even Tesla Powerwall data, which we've recently been toying around with to see if we can get some estimates from there. But it all costs time, money, etc. And then we've got the operational demand here, and this really exposes what I guess the inefficiencies of the ZIP and ZIP-DER models, because as you can see here, our DPV model estimated 94 megs of DER loss versus 113. So it underestimates it by 16%, but it's within range. The load model estimated 259 meg of load loss. The estimate was 338 with a range of 279 to 415 meg decrease. So it underestimates by about 23%. I purposely didn't want to go with a really good case because what I really want to show is that it's still a work in progress. And then you've got your operational demand as well, which underestimates by about 28%. But again, a lot better than if we were to use the ZIP and the ZIP-DER models. So this is one of the more, I guess you could say, a worst case scenario, but still an awesome result. So what this shows here is that overall operational demand decreased from 2,600 to 2,350 estimated by the PSSE models, whereas we think it's somewhere in the region of, say, 2,250. So it might be 100 meg off or so. In terms of model performance, so I've got two of these here. I won't go into too much detail, but this gives you a sort of overview of the voltage disturbances that we looked at, the events we looked at, the percentage of the observed value. So if we, for example, 8th of March, we saw that there was 100 meg of load loss. The model estimated 110 meg of load loss. And then you've got your uncertainty bands here as well. So it could have been 125% of our estimate all the way down to 60% of our estimate. We're not sure how much load loss occurred, but it's somewhere in that region. So the model's doing well. So in blue, you've got the composite load model. In yellow, you've got the DPV model. In red, you've got a combination of the load and DPV, which gives you your operational demand. And then you've got the sort of minimum values and maximum value. which is the accuracy of the models relative to the disturbances that we looked at. So the way that an NSP or AEMO or a consultant wanting to understand the dynamic response plus the amount of operational demand change in a region or a sub-region within that region, they can look at they can use the CMLD and DER models to run the simulation for, say, a worst case credible fault. They can get a value, say the operational demand change is 100 megawatts decrease. They know using these min and maxes that it could be anywhere from 70 to 105% of that estimate based on our results. So that 100 meg could be anywhere from 70 meg operational demand change to 105 meg of operational demand change. And once they know that, they can do things like set contingency sizes accordingly, set FCAS levels accordingly, and I guess overall make the market more efficient. We did something similar for the frequency disturbances and got similar results. This will all be published in our composite load and DER report, which is due to be released publicly in the next month or so. But as you can see here, the combined composite load and DER model for frequency events is accurate to within 60% to 110%. So minus 30, sorry, minus 40 or minus 30 or something like that, and then plus 10. So again, for an operational demand change of 100, you might say, okay, these are the error bar error limits. So it could be 70 meg, could be 110 meg. So to wrap up, the energy market operator uses these models to improve the way we calculate things like contingency size estimates, and as well as looking at contingency FCAS or frequency control ancillary services, the estimates, and then we can, I guess, have a more efficient market. We don't need to hold as much FCAS if we use these models, and that's what they're saying. We can also, I guess, the energy market operator, the network service providers as well, so your PowerLinks, your Ausgrid, etc., are able to use these models to understand how our grid infrastructure can be better supported by DER models, by distributed PV, and then where that support is needed, they can sort of perhaps provide an incentive to have people that live in that area adopt rooftop solar or battery storage or whatever it might be. And then we're also working with NSPs to redesign UFL schemes, so that's under frequency load shedding schemes, and redesign and also assess the limitations of over frequency generation shedding schemes, given I guess the content that the DPV and composite load models bring to light. In terms of next steps, we're doing a due diligence on the models now with an external consultant who was heavily involved in the development stage of the composite load and DER models in the US. And then at the same time, we're also running plenty of studies to assess the impacts of DPV on system security. And then we're also implementing long-term operational measures as well based on the findings of these models in PSSE. Longer term, we're going to continue refining these models, both DPV and load models. We're also rolling out these models in PSCAD, which is an EMT model specifically, and we're also rolling out these models in Dixlant's Power Factory software for the Swiss. So that's to come in the next 6 or so months. And thank you to the gentleman that asked about the battery energy storage, because we're planning on building a battery energy storage model as well, which we hopefully can translate across to EVs as well, because of the impact that these distributed energy resources will have on the grid. And that sums up my presentation. Thank you everyone for listening. If anyone's got any comments, please ask away now.
Thanks, Philip. I have a question. Here in Western Australia, we are doing some governance arrangement as well. So in Swiss, they are planning to introduce distribution system operator and distribution market operator and some aggregators. So I believe in future when there will be still more penetration of rooftop PVs, some of this work will be like maybe monitored or managed by the aggregators or distribution market operators. So are we also looking at how this will be managed in future when there will be like tenfold increase in the rooftop PVs?
Yeah, absolutely. The most pressing issues were initially for us low demand periods, high DPV generation levels. More recently, we've been looking at sort of a longer term approach. We're also trying to roll these models out to be used by NSPs and consultants and to build off of them. So right now we've got a particular NSP that is using our DPV models, and then because they've got more intricate level data, they're able to better separate our DPV models that we've got into their distribution network, because they know where the DPV sits. So rather than having, you know, let's say 30 meg on a particular bus, they might split it across 3 buses on the distribution network because they know that it sits there. In saying that, is this work going to be, I guess, handballed over to NSPs? I think we're working in unison with them and would like to continue doing so. But with the rise in, you know, energy storage, grid scale and residential, you've got, and rise in EVs, rise in DPV adoption. I mean, there's such a pressing need, and the more people that we can get working on it, using it, the better.
Could I just pick up on that point in terms of getting more people working on it? Are you happy to share the models internationally and get some collaboration outside Australia?
Yeah. So we have been collaborating with a few, I guess, equivalent market operators. We've spoken to California. There's been some discussion with the US as well, and collaboration. Germany, Ireland, South Korea. So there's been international collaboration there. It's just that, as I said, we moved away from their DER model because we've noticed the effects of our grid aren't able to be captured by our particular DER model. So we built a user-written model, which is more applicable to Australia. And since building that model, we've had a lot of interest internationally from other NSPs and other network operators wanting to use that. So there's a lot going on, but it all happens very slowly, if I'm honest, because people have, you know, a lot of work. They've got their full-time job going on, and then looking at this on the side, it's it's a slow process. But NSPs are more and more coming on board. Yeah.
Thanks.
So do you see AEMO recommending, say, generator connecting parties to use these models in their connection assessment as well in future? Because that's a whole separate sort of process.
Yeah. Are we going to recommend it? I'm not sure. Are we going to put it forward? We're already putting it forward. We're already walking through all the NSPs, all the TNSPs, DNSPs that are interested in hearing about it. We're walking them through how the model was built in a lot more detail than this 30 or 40-minute presentation. But at the end of the day, without, you know, stepping on people's toes, and we're trying not to go down that path because it should be a collaborative thing, and it should be it is something that will benefit the NSPs that choose to adopt it, and they're seeing that, and those that have seen that are miles ahead. But will it be legislated or recommended? That's above my pay grade, unfortunately. Yeah.
All right, thank you. Just as a follow-up, so where do you not recommend to use this model? I know you've talked about where to use it, so that such as system as a whole, but where should we not use it?
In terms of not use it, it depends on the amount of data you've got, right? So if you're doing a motor starting study and you've got the motor data, you just use the motor data and use an individual motor model. If you are trying to model utility scale DER, you can use the model, but you can also use the existing REG-C, REG-C, REG-B, whatever the models are called. There's plenty of them in PSSE. You can use the existing models because they are more, I guess they have more intricate level data. So this is an aggregate model, so it'll show you the aggregate response of DPV of composite load. So if you want to have a look at the aggregate response, then you would use these models. But if you can model it bespoke and individually, because it's not going to take all that much time, then I'd always suggest going down that route, if it's economically feasible, of course.
Thank you.
Any other questions? Now, for those that are interested in using the models, having a play with the models, any documentation released by us, please let me know, or at least pop your email down in the chat box, or speak to the organisers, and yeah, I'll reach out to you and hand over the models once they're publicly released in a month or so.
Thanks, Philip. Thanks everyone for your time today. We look forward to welcoming you at next IES webinar. Have a great evening, everyone. Thank you.
Awesome. Thank you. Thank you for your time all.
Thank you.
Thanks.